All right, let's try this again. Hopefully, this will work. So this is Ms. Ford, and we are going to be looking at the intro to immunity and starting the innate as well. So we're just going to have a nice overview, but then we're also going to talk more about the innate. So I titled this Defending the Castle. And so when we're defending the castle, we have the castle wall. And as we have the castle wall, we see the idea of the innate. We have the barrier defenses. So let's start with the goal of an immune system. The goal of the immune system is to be able to differentiate between self and non-self. So if you have a handy dandy little stomach cell, the stomach cell would be self. And then if we have this little bacteria cell, this is non-self. So how do we know to attack the bacteria cell but not the stomach cell? Well, that's the job of the immune system. Now, for the phagocytes that are going around, they're going to be able to recognize that this is to be ignored. We do not attack the self, but we want to get the bacteria. So, how does this happen? Well, we're going to be able to do that by recognizing a broad range of molecules. And the broad range of molecules would include things like double-stranded, double-stranded RNA, maybe from a virus, maybe a part of a lipid membrane of a bacteria. And these are all things that all animal cells should be able to recognize as non-self. So innate is something that all animals share. We're going to look at non-specific molecules that we don't know whether or not it's from measles or from HIV or mumps or the common cold or the flu, but we know that it's viral. So is it a kind of DNA that is unmethylated, so it's not something that animals have, but maybe a virus. And so we just kind of look at, okay, that's not us. And so we attack it, we label it for destruction. So the advantage of innate is that it is rapid. Now, the the disadvantage is, well, it's not specific. So if there's something that can get around it and get into cells before the body can take care of it, it's going to cause problems. Now, the barrier defenses, the first one is going to be pretty obvious. We've got the skin cells, and the skin cells are dead at the surface. And so we've got these cells, they're nice and flattened, and dead cells, because they do not have any working cytoplasm, viruses, can't infect them, and so they're good and protective for that. Now, bacteria and things like fungal cells, they can grow on top, feeding on the dead skin cells. And if it's a nice environment, like maybe, you've been exercising a lot, your feet are nice and sweaty, well, you could get a bacterial infection or athlete's foot. And because they're just feeding off the dead cells, well, they can cause problems. So there are some limitations, but the skin does a really good job. We are exposed to a large number of pathogens that we do not get sick from because of those dead cells. Now, underneath those dead cells, we do have living cells, and these living cells are going to divide and push up those skin cells. And so, if something breached it, like a splinter, if you got a great big splinter and carrying bacteria, that's going to cause problems because now these cells are vulnerable. We've breached past the wall, that castle wall. Now, the same is true for mucous membranes. Mucous membranes are tissues inside of our body that, similar to skin, they've got nice thick layers. They're epithelial tissue, but without the dead cell layers. So think of like your inside of your nose, the nasal cavity, your mouth, your reproductive or urinary systems, where they open up to the outside, but they're nice mucous membranes inside of their eyelid. So they're nice and pink. We see them. They're a little bit more vulnerable because viruses can now infect them. They can cause problems. They're nice and wet, so it plays a good host for all of those pathogens. But we have our own defenses against that as well. We've got things like mucus that kind of sits on top of our nasal mucous membranes and sweep away. Tears have a natural antimicrobial. They also sweep away. Hydrochloric acid kills bacteria and viruses, quite a lot of them, not all of them, but it does a good job. And even sweat has a pH anywhere from 4 to 5, hopefully, naturally, as long as we're healthy and we're maintaining that, that's going to create like a nice shield on our skin to kind of ward off the bacterial growth and like fungal growth. It's going to be very helpful. So all of these things help with the barrier defenses. Now, if it got inside, then we have what we would say are the sentries. They crawl around our body. We have these in really specific areas too, like our lungs. We have these macrophages that crawl around, and these are sentries. And so these sentries basically look out for anything again they don't recognize. And if their MO is going to be I don't recognize you, therefore I will eat you. And so we have these phagocytic cells that crawl around, these natural killer cells that can crawl around, the macrophages. These are all kind of very similar in nature. They go around and they recognize things that are non-self. Now, they can do a couple of jobs. They can, number one, they can eat them, and then they can serve as warnings. They can go back to the specific, and then they can call upon the cells that are going to be the specific soldiers. They can also, in general, raise an alarm call to basically say, we need help. And so they can create or signal the production of antimicrobial proteins. And these are just going to again be generic. They latch on to certain receptors or signal for destruction. Eat this, and they're going to serve to kind of advance those general soldiers. And we also have inflammatory responses whose job it is to kind of create a shield of white blood cells or cytokines, which call again these little chemical signals that from the breach of the splinter, these chemical signals call upon other white blood cells. Now, waiting in the behind the scenes would be our adaptive or specific immunity, and this we see with vertebrates. Vertebrates have adaptive and specific uh, immune cells. Now, these, just as the name implies, are going to be recognizing specific molecules that belong to specific pathogens. And we're going to take a look at how that happens. It is slower because, as a natural state, they exist as a dormant. So you've got these cells that basically are kind of, they're sleeping. I was trying to draw sleeping. There we go. They're sleeping, and hopefully we will never get exposed to Ebola. But if this little guy is Ebola and we never are, well, he's just going to be dormant for all of our life. But if we did get exposed to Ebola, the hope is that this little guy gets called into action very fast. Now, the problem with a lot of illnesses is while this guy gets called into service, the disease progress can really cause problems. Now, once these things get activated, we have two branches. One's called the humoral branch of the adaptive immune system, and humoral is an old word for fluid. And so, kind of the area around the cells. So the humoral branch is going to take bad guys, take care of the nice specific term that they're going to take care of bad guys that are outside the cell. And then the cell mediated is going to take care of the bad guys inside cells. Now, You want to hear my favorite analogy is that of a zombie movie. And if you've watched any zombie movie, most of the time they have this scene where one poor person in the group gets exposed to whatever that show has decided makes somebody a zombie. And if this poor cell or person is compromised, well, they have to go. So if this stomach cell is making viruses, and remember that's what viruses do, they cause the cell to make new viruses. Well, the problem is, as long as that cell is alive, it's going to be making viruses that can then infect neighboring cells. So this cell now needs to be gone. It's and just like the zombie movies, that poor guy has to be gotten rid of, and so we need to get rid of the pathogens inside the cells and then the pathogens outside the cells. So that's what we're going to be looking at. So hopefully that's a nice introduction to the immune system, and then we'll look at each branch separately.